segment 4. So starting to put together those electron configurations, and now we're ready to put the electrons into our atoms. So our electron configurations have to be consistent with the Pauli exclusion principle. Remember, that means only 2 electrons per orbital, ms equaling plus 1/2 and minus 1/2. We have to obey the Aufbau principle, which means we always start at the lowest energy in the orbital and slowly build up one by one. Okay, so we'll move up, filling up each orbital as we move. Then we have Hund's rule, 1 electron in each orbital of the same energy, so that the spins are parallel and they'll only pair up when they have to. So where are the electrons? Well, each box represents room for an electron, and we'll read it from left to right. So here, when we're looking at our periodic table, we can see that n equals 1, then we have hydrogen and helium. When n equals 2, we have lithium, beryllium, and then we also have boron, carbon, nitrogen, oxygen, fluorine, and neon. So again, you can see it's just like counting through the periodic table and putting together the electron configuration at the same time. All right, so we'll read the periodic table to determine the electron configuration of helium. We're going to read it from left to right. So the first electron would go into period 1. The first type of sublevel to fill would be the 1s. And so we'll put 1 in here and 1 in helium, and that gives us 1s2. Okay, moving right along to boron. Now we're going to have 5 electrons. The first shell will be that 1s, so we'll get hydrogen and helium. Now we're going to fill the 2 subshells in the second shell. So first, we're going to do lithium and beryllium. Then we're going to go across, and our 5th electron would represent the boron. So we're going to have 1s2, 2s2, 2p1. So we're always starting at hydrogen and working our way down to the element that we're actually performing the configuration for. Now, write the correct ground state electron configuration for each of the following elements. List in order of increasing n, and within each shell increasing L. So 1 would be potassium with 19 electrons. Okay, so we're going to start at hydrogen. We're going to get hydrogen and helium. That's going to be 1s2. Then we're going to move down to the second period. We're going to fill in lithium and beryllium. That's going to be 2s2. And if you couldn't tell, I just got my periodic table out, so I'm following along just like you guys. All right, so that's going to take care of 1s2, 2s2. That's 4 out of 19. Then we're going to skip over to boron. We're going to go boron through neon. That's going to give us 6 more electrons, and that's going to be our 2p6. Then we're going to go down to the third period, and we're going to get 3s2. Then we're going to go across and get aluminum to argon. That's going to be 3p6. And then finally, we are going to be at potassium, which is going to be 4s1. So our electron configuration then would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. All right, how about nickel with Z equaling 28? And again, you might want to pause, and then you can go ahead and give it a try. And then hopefully you got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Now you can see in the second line here, we've switched the S and the D around. That's really kind of up to you all. When I write the question, I'll be writing it that you'd put the answer in the order in which we do it from the periodic table or the electron chart, the flow chart there, which means my answer, I would have expected you to give me the 4s2, 3d8. It is proper notation to keep the energy levels together. So a lot of times you'll see people do this where it goes 3s2, 3p6, 3d8, 4s2. Again, linking it by the energy level. All right, how about lead with 82 electrons? Again, you might want to pause, give that one a try. Don't forget your f orbitals down at the bottom. All right, hopefully you've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Then we're going to jump to that f at 4f14, back up to the D, where we get 5D10, and finally 6P2. And again, if you want to rearrange to get the energy levels correct, we'll move the 3D10 over with the 3P6, the 4D10 with the 4P6, the 5D10 with the 5P6. Okay. All right, the next thing we want to do then is link up chemical reactivity with what we're seeing for electron configuration. So we know that the periodic table is arranged by chemical reactivity. And so that's going to depend on the outer shell of electrons, the highest value of N, which is the other reason why we may rearrange to get those highest energy levels. It's going to give us a little bit of insight into how things are bonding. Each row will be a different N. Now, there's also core electrons. These are going to be the inner electrons, where those with the N is less than N of the maximum. So if we're looking at that lead and we're in the 6S and 6P, everything underneath of that would be a 5 whatever and down. Those will all be considered core electrons. You can think of them as being buried deep inside the atom, and so they're not going to react and they're not going to do anything. So a lot of times what we're going to do when we're looking at noble gas, or excuse me, looking at electron configurations, is we're going to go to the noble gas that's closest and then complete the rest of the configuration. So we'll take the noble gas of the previous row, we'll put that in brackets, and then fill it in with the remainder of just that outermost energy level. So basically we're going to represent the core with that noble gas, and then the outer shell will be the ones that we can actually see. Okay, and we'll use that to emphasize that only the outer shell of electrons are going to matter. So for instance, if we were looking at barium, if you look at your periodic table and you find barium, right, we're way down here, number 56, it's in 6S. So what we're going to do is we're going to use xenon, put that in brackets, and then we know that's going to be our core all the way to there. And now we have 6S2 left over. And of course, that's a lot easier than writing 1S2, 2S2, 2P6, 3S2, so forth and so on, right? Ruthenium, same way. Sulfur, a little smaller, but still the same idea. Now remember, the other thing this is going to let us do is look at just the energy levels that are going to be reacting, right? So just the ones that are going to be involved in any kind of bonding. All right, so the noble gas notation for manganese. All right, so the noble gas of core notation for manganese then. So if we want to do manganese, what we're going to do is we're going to find manganese. So manganese is number 25, it's right here. So then we're going to find the noble gas that came before it, which is going to be argon right there. The argon's going to go in brackets. Then we're going to see what follows it. So after argon, we have potassium and calcium. That's going to be our 4s2. All right. Then we're going to look at manganese, and we're going to go 1, 2, 3, 4, 5. And so that's going to be 3D5. All right. Easy peasy lemon squeezy. All right. So the ground state electron configuration for calcium then is which one of the following? So again, we'll look at our periodic table. We'll find calcium. The core before that would be argon, and calcium would be 4s2. So that means we would use argon 4s2. Okay. Now this one looks like it could be it until we get to right there. Notice we only have 5 electrons in that P. That P needs to fill before we go on to that 4s. All right. So look at group 2A. So if we look at our electrons and we look at the abbreviated form, you can see that they all have what we call ns to the 2 outer shell electrons. So they all end in an S2. So we'll refer to them as S2 electrons. The only difference was going to be their value of N. And so this gives a little bit of insight into why compounds, or I should say elements, react and bond similarly to the ones that are in the same group. All right, so if I look at any group, this should be true. That outer electron configuration will look exactly the same, except for the N value will be different. As I move down the group, it'll grow by 1 each period, or each period I go down, right? So an element with the electron configuration Xe, 4f14, 5d7, 6s2 would belong to which class? Example like halogen, alkali metal, etc. on the periodic table. Now remember, what we can focus on is the total number of electrons, right? So don't get caught up, because remember we put them back in order by energy level. So if you look at the 6s2, you're going to be tempted to say that it's an alkaline earth element. But that won't be true if you look at the D before it. So the 5d7 isn't full yet, which means if we're in the D block and the D's not full, it must be a transition element. All right. So next we're going to look at a shorthand for orbital diagrams. So we can write out lines for orbital beyond the noble gas, higher energy orbital to the right, and then we'll fill from left to right. So abbreviated orbital diagrams look something like this. For the ruthenium, what we'll do is we'll say Kr, and then we'll just do the 4d, 5s. So rather than doing 1s, 2s, 2p, 3s, 3p, blah, 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 we'll simply look at the ones we're going to be involved with, which is the 4d, 5s. So something like sulfur then, we'll give the core neon, and then we'll show the 3s2, 3p has 4. And so again, you're going to try to pay attention to that when we go into different bonding theories in later chapters. This idea is going to come back, and you're going to find that it's very useful. At least hopefully you'll find that it's useful. All right, Valence Shell Electron Configurations. Last type of electron configuration. We'll use these mainly with the representative elements. So this is your S and P block elements. Here, only the electrons in the outer shell are going to be important for bonding, which means only the electrons in the S and P subshells, right? And of course, we call that our valence shell. It's the occupied shell with the highest. Okay, result, use even more abbreviated notation for electron configurations. So tin then, rather than saying tin and then showing an noble gas, we'll literally just say 5s2, 5p2. And now we know it's a group 4a element, and then everything that we know about group 4a would apply. Okay. Now, a few exceptions to rules. If you notice that chromium, copper, silver, and gold, they all play a different game. Okay, so the expected for chromium would be argon 3d4 and then 4s2. But looking at different experimental studies and energy studies, it turns out that what we see is argon 3d5, 4s1. And for copper, we see it happen again, 3d10, 4s1. Silver, 4d10, 5s1. Gold, 5d10, 6s1. Okay, that's strange. None of these work out. Now, if you pay attention to what's going on here, if you look at the s's, they're all 1 out of 2. What's 1 divided by 2? Half. Very good. We call these half-filled subshells. So the way this works is this. If I start putting electrons in and I get to certain levels, we get extra stability. And it turns out that when we get to half-filled, the energy levels drop a little bit. And so we get some stability there. When they're full, they drop some more. So the rankings then, if you will, would be a full shell is lower in energy than a half-filled shell, which is lower than any partial filled shell. So if I have half and I put one more electron in, it actually goes up in energy. So it becomes less stable when I put that other electron in. So we promote one electron into the ns orbital to gain this extra stability, right? So we're going to take, that's backwards, we're going to take one out of the s, put it in the d, and that's going to give us our extra stability. Now it's only going to do that if it can get half the D. So if the D is not moving to 5 or the D is not being filled, D10, then it will not do this. So if I have a D3, it's not going to take one electron and become an S1D4, right? It would rather have a full S, partially filled D, but if I can get half and half, it'll take it. If it can get half and full, it'll take it. Okay, so we always want to get rid of that partial if we can, but that's not always going to be the case. Sometimes we're going to just have a partial filled orbital. It's the way it's going to be. All right, so the orbital diagram corresponding to the ground state electron configuration for nitrogen is which one? So we know the 1s has to be full. That eliminates both A and B. Then we know we have to have the 2s full. That eliminates E. And then we're going to put them, right, one in each box, so they're all the same energy. Good job. D is our answer. Which of the following choices is the correct orbital diagram for a cobalt atom? Okay, so you might have to go to your periodic table. We look at cobalt. Cobalt is number 27. Okay, so we're going to get argon, and then we're going to get 4s2, and then 1, 2, 3, 4, 5, 6, 7 in the D. So if we're going to get 7 in the D, that means we have to have 5. Right, so we have to have 5, so this one's out, this one's out. Here we have 5, then that's only got 1 there. We're not going to do a half filled, right? That's not going to work out, which means it has to be E then, based on that. And it is, of course, E. All right, Excellent. So that's pretty much it for our electron configurations. If you have questions, make sure you get in touch with me. We can go through it again. Once you recognize the pattern, you'll notice that it gets pretty simple. So it's, I don't know, electronic configurations. One of the things I hear a lot of students say is it really this easy? And the answer is yes. Just if you use the periodic table, follow the pattern, it is actually that easy. And then of course, for us in 150, you can use the electron configurations to then observe, it would be the best word, back observe, I don't know, reflect. You could reflect on those quantum numbers and make sense out of the quantum numbers from the electron configurations and understanding the pattern. All right, the next thing we're going to look at is Heisenberg's uncertainty principle. And what Heisenberg said was that you can't know both exact position and exact speed of subatomic particles simultaneously. Okay? Such measurements always have certain minimum uncertainty associated with them. So the problem is this. I have this little particle and it's moving around. And so what he's saying is if I want to know where that electron is, I have to use a particle to figure out where it is. So I ping it, boom. Now when I hit it, what's going to happen? Well, the particles are so small, I'm actually going to move the momentum of that particle. So I no longer know the direction the particle is moving in. So either I can know where it's going, right? Or I can know, so I can know its speed, or I can know its position, but I can't know both. All right, so delta x, delta mv has to be greater than or equal to h over 4 pi. Delta x would be the uncertainty in the particle's position. Delta mv would be the uncertainty in its momentum. And so what we're saying is if we have its particle position and its mass and its velocity, then of course that would be the uncertainty. And then Planck's constant would be 6.626, of course, times 10 to the negative 34. Now, on the macroscopic scale, errors in measurement much smaller than measured value, right? So Heisenberg's uncertainty principle kind of goes away on the macroscopic scale, right? So if I have two cars and I know the directions and where they're going and I slam them into each other, we kind of can see what's going to happen and we can measure that. So really, we're only talking about the subatomic scale. So here, the errors in your measurements are going to be equal to or greater than your measured value, right? So it's getting right to the heart of accuracy and precision. So in the macroscopic scale, the error in your measurement is smaller than your measured value. That's why we're able to do that. But in the subatomic scale, it's not. So if you know your position exactly, then you can know nothing about the velocity. And if you know the velocity exactly, then there's no way you can know anything about the position. Okay? All right, so what are the following objects in order of increasing uncertainty in position, assuming the uncertainty in all of their velocities are the same? So again, we're looking at the textbook, the electron, the cell phone, and the sulfur nucleus. Okay, just give you a few moments to look at these. So order the objects, following objects in order of increasing uncertainty. So the only way you're going to be uncertain about where your textbook is if your memory forgets, right? So we know textbook has to be first. Then after that, it's probably your phone. And then is it the sulfur or is it the electron? And of course, the nucleus will be larger than the electron. All right, so what's the consequence of Heisenberg's uncertainty principle? Well, that means you can't talk about absolute position. You can only talk about electron probabilities. And so we say, okay, the electron is probably in this area. Okay, so where's the electron likely to be? And that's where our wave functions come in. Okay, so we call that psi. Psi is the wave function, and it's the amplitude of your electron wave. Now, psi squared then is going to be the probability of finding the electron at a given location. The probability of finding an electron in a given region of space equals the square of the amplitude of a wave at that point. And what that's going to do, we're not going to go into the math. You guys are probably, some of you I definitely know are more versed in math than I am. I know a couple of you are studying higher level calc. I don't remember that stuff, I'm not going to lie. But when I was in school working towards this, we would end up using calculus to come up with the electron cloud. So we could take that wave function, we'd run some integration from 0 to infinity if you would, and actually we wouldn't do infinity, we would do the 80% level, and that would work into our wave function so that we would develop the electron cloud. And this gives us a picture of what it would look like. So it's an electron dot picture, basically snapshots. It would be lots of dots by large amplitude of the wave function. And so what that's going to give us is a high probability of finding the electron. We call it an electron density. Okay, and it's electron densities are going to give us pictures of what the electron clouds would look like. And of course, the electron cloud is where we're most likely to find the electron. Okay, so how much of electron's charge is packed into a given volume? So if we want a high probability, then we have a high electron density or a large electron density. Okay, if we want low probability, then we're going to have a low electron density. So if we're looking at a 1s orbital representation, what we're going to do is this. We're going to do A. This would be like our electron cloud. So we're looking at all the high functioning areas of where, according to the wave function, we would find an electron. Okay, and we call that a dot density diagram. Now that's the probability of finding the electron around a given point. Okay, now the radial probability distribution is the probability of finding an electron between R and R plus X from the nucleus. Okay. So here's your distance from the nucleus. You can see we're going to find some maximum peak, and then it's going to be less likely to find it. So remember, we're trying to do a 2D picture here, but realistically this is a 3D image. Okay. Now R max would equal the Bohr radius. So if we go back and look at Bohr's idea of it being a solar system style, planetary style, the s orbital is going to end up being like a ball. Okay. All right, now your electron density distribution, that wave function, comes down to these three quantum numbers: the shape, the size, and the orientation. Now the electron density, no sharp boundary here. It's going to be a gradual fade away. Okay, so that's why I said 80% probability. If we did 100% probability, it would actually encompass a huge volume. Okay, so the electron, so if I had like a little sodium atom right here in front of my face, the 100% mark, absolute knowledge of where all of the electrons are, would be well beyond the radius of the Earth. Okay, no, I didn't misspeak. The 100% probability to find the electron in the sodium that's on the tip of my finger would be greater than the radius of the Earth. Okay? So, but that's going to give us the idea shape. Now, imaginary surface enclosing about 90% of the electron density of the orbital. And of course, that percentage might have gone up. You're talking 25 years now since I was an undergrad. And again, at that point, our test questions were taking that wave function, running psi squared, figuring out the electron probability, and then plotting it on a graph paper. And it basically took 4.5 to 5 hours on a Saturday morning. Fun. Again, now, we don't need to get into that level. What I wanted you to understand the background to finding these electron clouds. So really what I'm going to need you to know is the shapes of the electron clouds. Okay, so you won't be doing any of the calculus behind this. The course is based in algebra, so don't freak out. If maybe you want to do the math, I don't know. If you do, check in with me. I'll see if I can find some questions from my old PChem textbook. But I'm imagining most of us don't want to do that, and most of us are going to be happy just knowing the actual shapes. So for an s orbital, s means sphere, so it's going to be a spherical shape. Now, in any given direction, the probability of finding an electron will be the same. Now, notice you have these nodes popping up again, right? So if we look at the 1s, there's a chance you're going to find it in here. If we look in the 2s, then there's going to be a chance you can find it, and then we're going to have a node, right? And so it's like a jawbreaker with a spacer, if you will. Okay. All s orbitals are going to be spherically shaped, hence s. Now, the size is going to increase as n increases. Okay, now remember, you're going to have these spherical nodes. So at higher NL, now have spherical nodes. Okay, spherical regions of zero probability inside the orbital. So in other words, the 1s and the 2s don't overlap, right? They get a gap in there. This is the node for the electron wave. Okay, so it's an imaginary surface where the electron density will equal 0. Now 2s, one spherical node, size is going to be larger. 3s, two spherical nodes, size is going to be larger yet. So in other words, that node is going to get larger each time we gap up. Okay. So in general then, the number of spherical nodes will equal n minus 1. So obviously if we only have n equaling 1, then we have no nodes, right? 1 minus 1. But if n is equal to 6, now we're going to have 5 nodes. Now your p orbitals go a little differently. So p orbitals, here you can see when we do it, and you can see why we call it a figure 8 now, right? So it's kind of got like a figure 8 look to it. And then we've got some more out here. Now they possess one nodal plane through the nucleus. So back that up. Wait a minute. So in the s orbital, there was not a node at the nucleus. that suggests that the electron could actually be in the nucleus. Sorry, theoretical bunny hole. We're going to stay out of that bad boy. All right, so electron density only one on two sides of the nucleus, which means now we have what's called two lobes of electron density. Okay, so all p orbitals are going to have that same overall shape. And of course, now I'm going to put it in 3 dimensions. So I'm going to wrap it around. Okay, so my p orbital is going to look something like that. So we have a constant probability surface for the 2p orbital. We have that node at the nucleus in both shapes. So the simplified p orbital emphasizing the directional nature of the orbital, right? So this would just be the widened lobes. And now we're saying actually no, there's going to be some repulsion there. So they're going to actually spread out as much as they can, get a little further away. Now all 2p orbitals in the p subshell are going to have that. Now remember though, there's technically 3 shapes in the p orbital. That's just one shape. Okay, so if I put all 3 of them together, it's going to look a little more like that. Give me a couple seconds to digest that diagram. So again, we have the green orbital line along one axis, the red orbital along another axis, and the yellow going along our third axis. Okay, so 1 points along each direction. So if we were to take them apart, we call them the 2px, the 2py, and the 2pz, right, based on the Cartesian coordinate. All right, for D, there's going to be 5 different orbitals. Okay, you notice the lobes get a little bit crazier there, but it is that same basic shape. So first, we have the dxy where they're lying in. We have the D, looks like xz they're using. Then a dyz. Then we have an x squared minus y squared. So now we're actually on the actual coordinate, right, on the axes themselves. And then we get this weird one, dz squared. Okay. So we have 4 with 4 lobes of electron density, and then 1 with 2 lobes, which is going to develop that ring of electron density around it. The result of this will be 2 nodal planes through the nucleus. Now, the number of nodal planes through the nucleus will be equal to L. I wouldn't worry about that too much. Okay. All right. Which sketch represents a PZ orbital? So basically, we need to be able to pick these out of a lineup. So the minute we see 4 lobes, that's a D. So we know it can't be that one, can't be that one. 1 lobe, a sphere, will be the S. We know it can't be that one. So now we've got this one and this one, which have the 2 lobes, and we're looking for the PZ. And so of course that means we want to be on the Z-axis, and so that's going to be letter D. Okay, so again, don't worry about doing the quantum mechanics and the wave functions and the calculus to figure out the shapes. We just need to be able to pick those shapes out. All right. Compare 2 electrons with lower. I'm sure it's killing more than just me. Compare 2. Oh, compared. Oh, actually, it's me. Compared. I can't read tonight. I'm getting tired. We don't want that. Just leave it the way it is. Compared to. Oh, erase. See that? I'm even forgetting how to erase. Whoops. Compared to electrons with lower principal quantum numbers. Electrons with higher principal quantum numbers. All right. All exist as orbitals that do not have lobes. Okay, so compared to electrons with lower principal. So let's say if we just say n equals 1 and n equals 5. All exist as, I'm sorry, that's a typo though, as orbitals that do not have lobes. No. Because we could still be looking at the S in each one of these, and then we have no lobes, right? They move in circular orbits around the nucleus. Well, that used to be the thought, but obviously we just saw the P and the D are not actually circular orbits, right? So can't be that one. Have fewer subshells. That's actually opposite, right? Fewer subshells would be the opposite direction. Have lower energy because they are closer. That's actually wrong too, which means it has to be E. Let's see. Have higher energy because they're further away from the nucleus. Yep, I got it. All right, so we're going to end this segment here. Pretty long one, 30 minutes in. Periodic properties, which will be the consequences of those electron configurations. And that will be coming close to finishing up the chapter. So Hang in there. We'll do one more segment, it looks like, and then you'll be all done the chapter. All right, stay tuned.